Hello. We are now solving systems by another method called determinants. We've already covered solving systems by substitution, graphing, and linear combination, also known as elimination. This method is very strange looking, but in many cases it's very quick. And it's different, so if you like to be different than most people, this is the method for you. So I'm going to select, for an example, a system we've seen before. This is one from the previous video. We already know that the solution is 31 over 5 3/5. So I wanted to pick one that we already know the solution of so that you can see that determinants really works. Okay, so to present this method, I'm going to first just use the method as someone with experience would do it, and then afterwards show you where this method comes from. Okay, so I'm going to solve for x first. And what's interesting about this method is that unlike substitution or linear combination, I can start off by saying what x equals. I won't have 31 over 5 immediately, but I'm going to have some expression here that I already know will equal 31 over 5. So I'm going to draw a fraction bar, and I know that in the denominator I have to write down the 4 coefficients from the left side of these two equations. The 1, the 3, the 2, and the -4. Those are the 4 coefficients from the left sides of the two equations. 1, 3, 2, and -4. And I'm going to do some sort of calculation with these 4 numbers in a second. But first, I need 4 numbers in the numerator of my fraction as well. I'm going to write 8, 10, 3, -4. Now, why those 4 numbers? First of all, I've simply copied down the 3 and the -4 from here up here. So that was just a simple copy. The 8 and the 10 come from here and here. That's where the 8 and the 10 came from. How you remember where to put the 8 and the 10, I'll talk about that a little later. So once my 8 numbers are down, 4 on the top, 4 on the bottom, I do 8 times -4 minus, must be minus, 3 times 10. And in the bottom, I do the same top left to bottom right multiplication. 1 times -4 minus 3 times 2. And then all I have to do is simplify all this stuff here. And I get my 31 over 5. Okay, now I'm going to find y, also using determinants. There's going to be a slight difference in the setup of the 8 numbers. In the denominator, I'm going to do the exact same thing I did over here. 1, 3, 2, -4. So you don't have to memorize anything new for the denominator of y. It's going to be the same as the denominator of x. In the numerator, I'm going to write 1, 2 here. That's just a copy of this 1, 2. And then over here, I'm going to put 8, 10. Okay, now I do the same thing. I do my crisscross multiplying with the subtraction. 1 times 10 minus 8 times 2. Denominator. 1 times negative 4 minus 3 times 2. Now I just simplify. And there you have it. 31/5 is x and 3/5 is y. Okay, now I'm going to give you a few pointers here that might save time. First of all, the denominator of each fraction is the same. This is the same as this. So I actually didn't have to do this again because it's identical to the denominator work when I was looking for x. So I could have just gone straight from here to here. I already know it's going to be negative 10. So that saves a lot of work. Also, I mentioned, how do you remember that the 8 and the 10 go there when you're solving for x, and the 8 and the 10 go here when you're solving for y? Well, the way I remember it is, in standard form, this is the x column, always. And this is the y column, always. So in the determinant, this is the x column also, and this is also the y column. So in the x column, when I'm solving for x, that is where I put the 8 and the 10 in the numerator, in the x column, when I'm solving for x. Conversely, when I'm solving for y, I put the 8 and the 10 in the y column. So that's how I remember it. When you're solving for x, put these two numbers in the column of that variable that you're currently solving for. Now, what about the rest? The rest is a lot easier to remember because the denominator is always the 4 coefficients from the given standard form equations. You just copy them down as they are, in the positions that they are. And then these numbers that you are not changing just are copied in the numerator. These are just copied from the denominator to the numerator. So that's how you remember the setup. Now, why does this work? It's so strange looking. Where did it come from? Well, it's kind of a misnomer to call this a different method because determinants actually comes from linear combination. And this is what I mean. Okay, so here is the generic form of two two linear equations in standard form. A, B, C, D, E, F are my constants. So A, B, D, E are my 4 coefficients, and then my 2 constants, C and F, are on the right side, just as we had here. Okay, so what I'm going to do now is solve this system by linear combination and see what we get. So I'm going to eliminate, I choose to eliminate the y's, okay? Their coefficients are currently different, so I need to make them the same. I'm going to multiply the first equation by E and the second equation by B. And I'm going to do that because my new coefficients for the y terms are then going to be identical. So I'm distributing the E now. now I'm distributing the B. Okay, you can see that the two coefficients of the y terms are now identical, so, and they're the same sign, so I will now subtract. No more y terms. Now, since I'm solving for x, I need to isolate the x. There's an x in two different terms, so I will use reverse distributive property to take one x out. And then divide both sides by AE minus BD. So that cancels. And this is what x is. So let's apply this to our problem up here. This is A, B, C, D, E, F. So x is supposed to be C times E, that's 8 times negative 4, minus B times F, BF. The denominator is A times E, 1 times negative 4, minus B times D, 3 times 2. That's negative 32 minus 30 over negative 4 minus 6. That is negative 62 over negative 10, or 31 over 5. Okay, so now you know that this formula works. And since I used a generic standard form equations where A, B, C, D, E, and F could have been anything, this will work in all cases. Now, when I was doing the calculations here, you probably noticed that these calculations felt very familiar. They were exactly what we did up here. These calculations here are exactly these calculations down here. So what does that mean? That means that these determinant calculations here that I showed you for the very first time was actually not a unique method. It is really linear combination presented with different clothing. Or I should say stripped down, because when you're doing linear combination, you have x terms and y terms and terms without x and y, and you're trying to eliminate variables, right? In determinants, there are no variables in the calculations. The obstacle of the variables has been stripped away in this method, and that's why some people prefer determinants, because they don't like to deal with the variables. But just know that this is where determinants comes from. It comes from linear combination. So why do we even do this stuff if it comes from linear combination? Well, the reason is, if you look at this formula CE minus BF over AE minus BD, it's hard to memorize. There's no pattern here, seemingly. It's sort of like a phone number that has random numbers and none of the numbers repeat. It's harder to remember than a phone number that has a pattern or has repeating digits. So someone had the bright idea of, why don't we put these letters, CE, BF, AE, BD, in some sort of formation where it's easy, or that doesn't force us to remember does CE come before BF or BF after CE? I can't remember. If we put them in some sort of formation where we don't have to remember that stuff, then it'll be easier to handle. So someone had the bright idea of, hey, I noticed that AE minus BD, the denominator, AE minus BD, is exactly what you would get if you multiplied these coefficients and then multiplied these two coefficients and then subtracted. And then someone noticed, hey, the numerator, CE minus BF, you would get that if you took these two values and then replaced the x coefficients with 8 and 10. And you would still do the x thing the same way you did in the denominator. So we would just have to remember one thing to do, the x thing, and then subtract. So it's just convenient that it works out like that, so that you don't have to memorize this clunky jumble of letters here. Okay, so that is solving systems by determinants. It's brand new for most of you. It takes practice. So make sure that you do practice determinants. You can take 2x2s that we've already solved by substitution or linear combination and do them again by determinants and see if you get the same solution you got before. Okay?